in this circulatory system, one of the biggest things that I'm trying to show to you now is the difference in their structures, the difference in the amount of this layer with the elastic tissue that's going to be present. One is under pressure, one isn't. We have valves that are present, okay? We have an outer layer, middle layer, inner layer. So these layers that are going to be present are termed tunics. Because just like everything else that we pretty much discussed, we've got the 3 layers. When we talk about these blood vessels, we have them, they're going to fall into one of 3 categories. Arteries are efferent. They take the blood away from the heart. Veins are afferent. They're bringing blood back to the heart. And then, of course, we have our capillaries, which are going to connect these the two vessels. When we talk, like I was showing in the picture, their histology, they have the 3 layers. They're termed tunics, okay, tunica. One's internal, one's middle, one's external. The outer tunic, the inner tunic, simple squamous epithelium. Simple, how many layers?
1.
Squamous, what's the shape?
Flat.
The flat, do what?
It's like the rectangular flat seals.
It looks like the fried egg, but I knew what you were trying to get to. So, the 1 layer of the fried eggs. Now, what could be the importance of that? Why is simple what functions or activities do simple squamous make easy to do?
Allow for like transport and like moving throughout in and out the cell for nutrients.
I have the ability for materials to move easily, i.e. diffusion. Now, where that plays a major part is here at my capillary level, because my capillaries are 1 cell layer thick. They are simple squamous, which if we think about this, this is the area exchange occurs. This is the area that materials in the blood can move out and waste from the tissues can move in. So, my internal tunic, there's a basement membrane. It runs continuous with my endocardium of the heart. If we think about those vessels that are leaving, their connection is this internal tunic from the heart. This makeup, if we go back to part 1 and think about simple squamous epithelium, this means they are selectively permeable. They control what goes across them. All right? They have the ability to secrete chemicals. One of the things that we need as the blood is moving through the vessels, we need to make sure that the blood is not going to clot. And these cells secrete chemicals that repel the platelets so that it does not clot in these vessels. When there's a time of damage, that of course changes. They actually release chemicals to bring in clotting factors. It's really cool. We talked about that, right? Okay. The middle tunic is our smooth muscle. There is collagen present because not all the vessels are going to be really stretchy. But in some, the elastic fibers are going to be dominating. If you remember, collagen is a very tough protein. It's a very tough fiber, okay? It's the structure for a lot of things in the body. Helps to strengthen those vessels and helps those vessels to withstand the pressure of blood leaving the heart because it's under pressure, okay? The external tunic is loose connective tissue. It'll merge with vessels close to them. It'll merge with nerves. What? Nerves? Do I need nerves with my vessels? Oh, yeah. It is so cool how the nerves innervate the blood vessels. It really is. It helps them merge to organs. It helps anchor the vessels so that they're just not moving everywhere throughout the body. Helps for giving a passage for nerves and lymphatics, which we'll be getting into. And then, get this. You guys remember how when we talked about the heart, we had our coronary circulation, meaning that even though the heart was doing the blood, it's still tissue that needed a blood supply. Well, guess what? Even though vessels are moving the blood, they still need a blood supply. They'll actually have vessels that come in and do a little twist and go back to feed the tissues of the vessels. I know, really cool, right? So, when we have that take place, it's going to be termed vasa vasorum. This is the vessels that are going to help nourish the larger vessels. Very interesting structure for this anatomy. When we talk about arteries, we're going to term them resistance vessels. Why? Because they can resist the surges of blood pressure. In this structure of the heart, when the heart beats, as blood leaves the right side and enters into my pulmonary trunk, okay? That's a huge vessel, okay? It's not under the same pressure as my aorta. My aorta from the left side is under tremendous pressure. And in all reality, difficult to determine the actual pressure because the closest we can get to it is here, the brachial, where we can do the blood pressure here. It's a good indicator of what's happening at the aorta, okay? But now this aorta, all right, that pressure that it has to withstand, it's based upon, like for example, when we take pressure, 120 over 80. And this is referring to millimeters of mercury. Why does it refer to that? No, anybody? Okay, what do you know about mercury? Definitely dangerous. Do you know?
Deadly.
Deadly. Well, okay. Give you an idea about mercury. All right, it's a heavy metal. Heavy being the operative term here. I grew up in the time when you had the glass thermometers, and at the bottom of it was the mercury. And when Mom would come and put that in, you had to leave them 3 minutes or whatever it was, and see, and then you had to be like all this, to try to read it and that sort of thing. And your temperature was based on how that mercury moved up that glass tube. Okay, well, when you're younger, like the little kids and stuff, like I was, and those constantly broke, okay, the little mercury would fall out. Well, that was cool because the mercury would roll around the table. Nobody was telling me that that was a heavy metal that was dangerous and could cause central nervous. Dr. Vines right there has known me for 20 years, and she'd probably be like, yeah, she played with a lot of mercury growing up. Okay, so we have this situation of this heavy metal, but based on the heat from my body, it could force it to move up that tube. Does anybody remember like really old ways of taking blood pressure? They'd have a cuff, there'd be a tube right here, and it would pump, and you'd have to watch something move up. The original one was based on moving the mercury up that tube. Mercury, heavy metal, and it would under normal conditions would move at 120 millimeters up that tube. Does anybody know what kind of pressure that takes? In other words, the pressure our heart is under. That's tremendous. I don't remember the weight of mercury right now off at the top of my head. I'd have to look it up. But it would be moving at 120 millimeters up that tube. All right? The aorta and the arteries, the larger ones, okay, the ones that we refer to as conducting, they have a lot of ability to expand and recoil because they are under pressure that is coming directly off the heart, of that contraction of the heart, the blood leaving. And then it has to move into smaller arteries, and on the aorta you can see that there's some branching that occurs. This is to be able to have the blood go up into the head and neck and into the upper extremities. And then it will begin to descend and branch. Okay? So, this direction right here, the blood has to move against gravity. It's under tremendous pressure as it begins to flow. As we begin to descend, gravity's helping. So arteries, I don't know if you've ever paid attention, but like the models that we have back there, they're trying to represent the size of these vessels that are going against gravity and the size of the vessels moving with gravity. Okay? So as it leaves the heart and we get to here, we check pressure, and as blood continues to move through these arteries and move, we go from very, very large, the largest, into large, into medium, into small, into